Chinese researchers have recently achieved a significant breakthrough on the lunar surface through their Chang'e 5 mission. The mission involved a sample returned from the moon. Chinese scientists have officially affirmed the unearthing of a new mineral within the lunar regolith, a translucent crystal, aptly named Chang'e site. This development marks China as the third nation, following the United States and Russia, to identify a fresh type of rock on the moon. Chang'e now stands as the sixth distinct mineral recognized to exist on the moon, yet still undiscovered on Earth. This discovery is of considerable significance, not solely because of the emergence of a novel extraterrestrial rock, but more importantly due to being a fraction of China's recent findings from their 2020 moon soil collection, acquired through the triumphant Chang'e 5 robotic lander mission. In their lunar regolith samples, the Chinese researchers also identified helium-3, a valuable isotope. This particular isotope of helium holds promise as a potential fuel source for nuclear fusion reactors. The Chinese scientists assert that they not only discerned the concentration of helium-3 within moon dust, but have also discerned the method for extracting this isotope from the collected samples. While the revelation of new lunar discoveries is a boon for scientific advancement, it's worth noting the concern that these discoveries are being made by China and not by NASA or another more transparent space agency. This particular revelation concerning Chang'e arose from a small assortment of lunar regolith, amounting to approximately 61 ounces of dust and rock extracted from the moon's surface by the Chang'e 5 rover and subsequently transported back to Earth in 2020. The rover successfully landed in a region of the moon designated as Oceanus Procellarum, translating to the Ocean of Storms. This region appears as a lengthy dark area on the moon's visible side, situated at the northwest corner. The specific sample in question was collected near Mons Runker, an area previously marked by volcanic activity, indicating the rock and soil's age to be around 1.2 billion years. Chang'e 5 employed a combination of mechanical scooping and drilling techniques, penetrating up to 2 meters below the surface. This differs from NASA's sample return mission in the 1970s, which procured regoliths substantially older, ranging between 3.1 and 4.4 billion years. None of the Apollo crew landings were in the vicinity of Chang'e 5's sample collection site. Within this sample, China detected a singular particle of colorless, transparent crystal, a petite, 10-micron wide entity akin to a diamond. This newly identified mineral, Chang'e, is categorized as a phosphate mineral and columnar crystal. It has received certification from the International Mineralogical Association as a newly classified mineral, one of 6 discovered in lunar samples. While the moon crystal discovery is undoubtedly fascinating, the real cornerstone of China's lunar sample findings is helium-3. Although not a novel concept, this isotope is acknowledged to exist in minimal quantities on Earth. However, there is a strong belief that it's abundant on the moon. Helium-3 is produced through the interaction of solar wind and cosmic radiation with the unprotected lunar surface, unlike Earth, which possesses a magnetic shield that deflects radiation. What makes helium-3 particularly noteworthy is its atomic structure, comprising 2 protons and 1 neutron. It's the only stable isotope known to have more protons than neutrons. Theoretically, a fusion reaction involving deuterium and helium-3 could generate an impressive 164.3 megawatt-hours of energy per gram of helium-3. To put this in perspective, the Hoover Dam produces around 11,000 megawatt-hours daily. Hence, about 67 grams of helium-3 could match the daily output of this substantial hydroelectric facility, an astounding prospect. Additionally, neither helium-3 nor its resultant products are radioactive, negating the generation of radioactive waste from reactor components. Currently, the most viable means of obtaining helium-3 is as a byproduct of decaying tritium isotopes in existing stockpiles of nuclear warheads. This is how it is collected today, yielding approximately 15 kilograms, 33 pounds, annually. Due to its scarcity, helium-3 commands a high price, exceeding USD 17,500 for a single gram. This isotope presently finds use in small-scale nuclear fusion experiments, medical imaging technology, and neutron radiation detectors employed at U.S. border crossings to detect nuclear materials. A momentous stride has been taken in lunar exploration. Recent revelations from China suggest an astounding breakthrough regarding the moon's surface. It appears that the lunar expanse is believed to harbor a staggering 1.5 million metric tons of helium-3. This helium-3 holds an immense value of around $1.5 quadrillion, signifying a resource of colossal proportions. This discovery could potentially revolutionize global nuclear fusion energy. Remarkably, a mere 100 tons of helium-3 could fuel this transformative power on a worldwide scale. China enjoys a substantial head start in deciphering the location of this precious helium-3. The Chang'e IV mission, positioned on the far side of the moon, is actively seeking out deposits of this valuable resource. Additionally, China claims to have already devised a method for extracting essential isotopes from lunar soil. Of course, the journey to harnessing enough helium-3 to significantly impact Earth won't be straightforward. The most concentrated helium-3 in lunar soil is estimated to be around 50 parts per billion. China maintains they possess precise calculations of the actual concentration based on their sample findings. However, they have chosen not to disclose these figures. Based on our approximations, processing a staggering 150 tons of lunar regolith would be necessary to harvest a single gram of helium-3. This formidable space mining endeavor is further complicated by the challenge of returning the extracted helium-3 to Earth. While these endeavors won't come to fruition shortly, they are by no means unattainable. China is currently deep into testing their Long March 9 rocket, a super-heavy lift vehicle poised to rival the SpaceX Starship in terms of both mass-to-orbit capacity and interplanetary travel capability. Anticipated to launch its maiden voyage between 2028 and 2029, the Long March 9 is projected to accommodate payloads of up to 150 metric tons to low Earth orbit, 50 tons to the Moon, and 44 tons to Mars. This paves the way for prospective lunar mining operations. China's ambitions extend beyond helium-3 discovery. Following the Chang'e missions and their helium-3 breakthrough, the China National Space Administration secured full state approval for a trio of subsequent lunar missions: Chang'e 6, 7, and 8. As early as 2024, Chang'e 6 will further explore the far side of the moon and pioneer the return of samples from that region. Chang'e 7 is geared towards investigating the moon's south pole to uncover water ice reserves, crucial for future human colonization. Chang'e 8 will introduce robotic technology to the lunar surface, laying the foundation for an international lunar research station, a collaborative lunar base orchestrated alongside the Russian space program. This visionary undertaking is plotted over the next decade. In the words of the director of China's Lunar Exploration Program, the purpose of our mission is to lay the foundation for building a lunar station. While substantial technological challenges lie ahead, China is optimistic about their abilities to succeed. On the flip side, NASA's Artemis program, aimed at re-establishing human presence on the moon, faces its own set of hurdles. Although Artemis strives to return humans to the lunar surface by 2024, 2025, or conceivably 2026, progress has encountered obstacles. The success of NASA's Space Launch System, SLS, rocket remains uncertain. Should the SLS encounter setbacks, China could potentially dominate lunar activities for the foreseeable future. SpaceX's Starship, designed to be a reusable lunar lander for the Artemis mission, could take the lead in such circumstances. While the outcome remains uncertain, it's worth acknowledging that China's dynamic lunar strides juxtaposed with NASA's prolonged lunar status quo may tarnish the image of Western exceptionalism. As global competition intensifies, only time will reveal whether China's dominance in moon-related advancements will reshape the narrative of space exploration, energy, and cooperation.